Welcome to lecture number 9. In the last two sessions, we were looking at the permeability or flow through porous media, as we call it, and we looked at basic fundamentals. We looked at what we call as permeability. It comes from the concept of flow through porous media. Soil being a three-phase material, we call it as porous, and it's a media. And we first looked at the basic concept of Bernoulli, which says it is the total head which controls flow, which is equal to elevation head plus pressure head plus velocity head. But in case of soils, velocity is so small, the contribution of velocity head is very negligible, so we don't consider that. So we say we need to consider the elevation from a datum and the equivalent of pressure head, which is nothing but the pore pressure by gamma W. This is how we do that. Based on the total head, way back in 1856, Darcy gave a famous law which says velocity is proportional to the gradient, where gradient, and let me specify, its hydraulic gradient is loss in head by the distance traveled. Suppose we have a stratum of length L, and if I put a piezometer here, the pore pressure is here, another piezometer, pore pressure is here, and if I look at the datum, I call this as H at A, point A, and here it is H, total head is B. But please remember, out of this is the elevation head at A, and this should be the pressure head at A. Similarly, if I look at it, this is elevation head at B and the pressure head at B, and the difference in elevation between these two, or difference in heads, is what you can call the drop in head or the head loss, which is what we had to consider here. And I divide by the length between the points A and point B, and that is what Darcy says the velocity of flow is proportional to the gradient. I defined as loss in head divided by distance between the points, or you can say distance of travel. So based on this velocity, you can calculate the rate flow. Q, the rate of flow, is equal to V into area. So K, permeability into I. Please remember, the coefficient K is called its units are in centimeters per second, meters per second, or you can say meters per year. Any one of these you can use. Because as you can see here, V is velocity, units are centimeters per second, I is gradient, dimensionless, so K has to be in terms of centimeters per second. The point I'd like to make, which I made last time, was this Darcy looked at the whole cross section of the soil. So this consists of area occupied by solid grains plus the voids. So he has taken the total area. So when I want to get the rate of flow or discharge, you want to call it, you have to use the cross-sectional area. Then you may ask, if the flow is only taking place through the voids, what will be the velocity? So that can easily be calculated, and found out that Vs is called the seepage velocity, which is equal to this average velocity by N, which is porosity. N is the porosity. So actually the seepage velocity will be higher because the porosity of the soil is always less than 1, maybe 0.4, 0.5, 0.6. So the actual flow velocity will be slightly more than the average velocity because of the term N, which is less than 1. Then we also found out that the coefficient of permeability we are talking of is a function of fluid properties. It's equal to, if you want to write, for example, unit weight of the fluid by the coefficient of viscosity into what they call as intrinsic or absolute permeability. This is called intrinsic or absolute coefficient of permeability. These two terms, they depend on the fluid properties, whereas K depends on the soil characteristics. What does it mean when I say soil characteristics? It means it's a function of the void space, size, shape, distribution, etc. K is a function of void, size, shape, void distribution. You may not have same void sizes, they can keep varying, etc. Plus what is called as tortuosity. Please remember, the flow will not be along a straight line, but it would be zigzag depending on how the voids are distributed along the length of flow. So this is basically a property of the soil, and we now add the characteristics of the fluid, and usually these are supposed to be functions of temperature because the density and the viscosity of a fluid are functions of temperature. But between these two, the viscosity is more sensitive to temperature and not density. So what is generally given is that the permeability is correlated with respect to temperature corresponding to 20. So if you want permeability at T is equal to 20 degrees, we'll have to calculate permeability at the temperature one is finding it out, and into eta at temperature equal to 20 divided by eta at temperature. In India, for example, in most of the places when we test in the laboratory, unless you have an air-conditioned laboratory, the temperature is likely to be more than 20, usually around 25 to 30 degrees, in which case the viscosity coefficient is different and you have to apply a correction for that. We looked at after this two methods of determining permeability in the laboratory. We have two tests. One is called the constant head, another is called variable or what we call as falling head. Variable head test and constant head test. This one is for coarse grain soil. Permeability is generally greater than 10 to the power of minus 3 centimeters per second. Whereas this is for fine grained soil, and we have discussed the same, so I don't want to repeat, but maybe I'll show you a small presentation on that later. What I would like to add now would be, apart from these tests, we have a lot of experience which has been given in the form of what we call as empirical relations. What people have done is they have tested a variety of soils, and based on their experience they have given the relationship between various parameters. One of the earliest was given by Hazen, a geotechnical engineer in charge of dams. He was looking at filters, etc. According to him, K is equal to C times D10 square. You remember we talked about D10 is the diameter corresponding to 10% passing. So if I have a grain size distribution, here I am plotting D and percentage passing, or finer they call, goes from 0 to 100. And let's say for the soil you are investigating, you have found out the grain size distribution. Now let's look at this 10% point and get what is called as D10. You can use either a small d or capital D. It doesn't matter. The reason is the smallest void or the normal void size will not depend on the big particle size. If I have a big particle, another particle here, etc., the void space here will be dependent on D10 and not on the large size. So Hazen said this may be the criterion, and he said the constant is around 1 to 1.5. And that's how you can calculate the permeability based on D10 and using a value. Again, please remember, all these are approximate. They may be very useful for preliminary design, but we don't use them for final design. For final design, nothing less than actual testing, either in the lab or in the field. Then another can derive this is through what is called as Poiselli's law. He was looking at flow through small tubes, and then based on that you can derive that K is proportional to E cube by 1 plus C. And there are some charts which are given for this kind of variation, particularly for fine-grained soil. So which means you had to find out the void ratio of the soil and then plot it. Based on again this Hazen's equation, we have several tests done later. I think one group is Kenny and his co-workers. Way back in 1948, they came out with similar plot, except they have given based on D10, 0.1, 1, 10, and K here is straight away given as in terms of feet per minute, varies from 0.1, 0.1, 1, etc. And they have found out a set of graphs as a function of void ratio, 0.7, 0.6, 0.5, 0.4, 0.3. And you can see here now the permeability is not only a function of D10, it's also a function of void ratio. Something combining these two equations, you get a relation, because you may have the same soil with a grain size distribution, but I can arrange them at different void ratios. If I have a loose packing, void ratio is 0.7. If I have dense packing, void ratio can be as low as 0.3. So for the same D10, if I do that, you can see that the permeability values can be very significantly affected by the void ratio. So please remember, this is a very important improvement. K is a function of not only the grain size distribution, but also function of void ratio. Sometimes you may say in terms of packing. I told you in one of the earlier ones, I can have the grains sitting on top of each other, in which case the void spaces are very large, or I can have the extreme case, grains sitting in the valley of the lower row, which means the void spaces are much smaller. So based on the void ratio, you can also find out, and this chart is available in the book by B.M. Das, which is one of the textbooks for us. So I would like you to keep this ready with you whenever you are doing a design. Similar to this, for clays, we also have another empirical correlation. This correlation also is a function of uniformity coefficient. You can have, this is for uniform sands, and Kenny and other group, they have given another chart for well graded. So you have different estimates based on the uniformity coefficient. If you remember, uniform means poorly graded, CU is somewhere between 1 to 3. Well graded means the coefficient of uniformity is greater than 4. So if you have well graded soil, you have one correlation, and for poorly graded or uniformly graded, we have another formulation or empirical relation. For clays, we have similar relation. We have void ratio here and permeability in meters per second. So please remember, depending on how somebody gives, it can be a different set of units. And we have void ratio varying from, let's say, 0.5 to something like 2. What you find are set of graphs like this, set of curves, which correspond to Pi plus clay fraction CF is equal to 1.25, 1, 0.75, 0.5, etc. What does it mean? Each curve corresponds to a particular plasticity index plus clay fraction. So for different types of fine-grained soil, plasticity index can vary from 0 to, let's say, 40 or 50%, which means maximum 0.5, and clay fraction again can vary from 0 clay to maybe 80% clay. So look at the fractions and add them up. You will get a value somewhere. for a particular, let's say, void ratio of something like 1.5 and 0.8, you will immediately get this to be somewhere around maybe 8 into or 9 into 10 to the power minus 10 centimeters per second. Multiply by 1000 or 100, you will get centimeters per second. As I said, for clays or fine grained soils, clays, K is less than 10 to the power minus 6 centimeters per second. So that corresponds to less than 10 to the power minus 8 meters per second. You know that, and this is how we try to get a rough estimate of the permeability based on experience of all our practicing engineers and those who have actually determined the permeability for various soils in their project. Then we'll pass on to another very interesting aspect of permeability or flow. Flow, for example, whenever we do the testing, if you remember, the flow can be vertical, either downward or upward. This is a downward flow and this is upward flow. But in practice, it can be anything. For example, if I have an earth dam storing water, the flow will be both horizontal and downward. Or if I look at a gravity dam, the flow can be downward, horizontal, upward. So which means the direction of flow is variable. The flow can be downward, it could be inclined downward, it could be horizontal, it could be inclined upward, or it could be purely upward, which means the permeability values should be found out for different directions. You know that from simple mathematics, if I know the values in two orthogonal directions, you can easily find out for any third direction. This is x direction, y direction, and we can find out. So what it means is there a directional dependence of flow? And then what you do then is, suppose I want to test the permeability in the vertical direction. I take a sample, pushing the tube in the vertical direction. If I want in the horizontal direction, the tube has to be pushed horizontally. Same thing here, I can push the tube vertically, or I make a pit and then push it horizontally, so that the directions are different. So what you find is, if I call Kv is the coefficient of permeability in the vertical direction, and Kh is coefficient of permeability for flow in the horizontal direction. And these two values are not necessarily equal. Kv is not equal to Kh. What does it mean? It says the coefficient of permeability for flow in the vertical direction need not be the same as the coefficient of permeability in the horizontal direction. So you can actually plot them and then see, if you do the tests in loose sands, we find that Kh is greater than Kv, whereas in dense sands, Kh is less than Kv. The reason is, in dense sands, the particles are all packed so that the flow is highly irregular. It cannot be horizontal. The voids are not very well connected. So compared to the flow in this direction, the flow in the horizontal direction will be more difficult. In case of loose sands, the flow in this direction is easier than flow in the vertical direction. So for example, if I plot the ratio permeability Kh by Kv as a function of void ratio, higher void ratio, the permeability ratio will be more than 1. That means loose soils will have more horizontal permeability than vertical one, whereas for dense soils whose void ratio is less, the ratio will be less than 1 because Kh is less than Kv. Similar things happen in case of fine-grained soils also. This ratio Kh by Kv can vary from, let's say, 0.5 to 2, which means the horizontal permeability can be less than vertical permeability or more than permeability, depending on the compaction conditions, the void ratio, etc. We also have this problem if you have layered soil. Suppose we have layered soil or soils whose is a function of depth. Let us say at a particular site you have soil layer 1, permeability is K1, layer 2, permeability is K2. Each layer has its own permeability, K3, etc. You can have any now. We also tried to do this. Suppose I find with respect Z, I divide this into number of layers and then find out the average permeability and say it is all because of stratification. You have found out permeability at different depths, may not be constant, it can be variable. There are some soils in which K, that's the depth. It can vary something like this. You have a sand layer, a clay layer, sand layer, clay layer, etc. In which case, how do we handle this? Do I have to take all the layering effect, or can I get an equivalent permeability? This is very easy to find out. For example, let us say we have a simple situation of set of soils. So I'll put it K1, K2, K3, K4, let's say Ki, and last one is Kn. And thickness can also be variable, H1, H2, H3, H4, Hi, Hn. Let us say I have a reservoir here and the flow is taking place along the stratification, and this is the downstream water level and the water level is somewhere here. So the head loss is H and the distance between these 2 points is L. What you are saying is I have flow. This is a typical case of flow below a gravity dam where you have layers of different permeability. So here is the upstream reservoir level, water is flowing here, and this is the downstream reservoir level, water level. So this is the head loss, H, across the dam. So we would like to know, should I use all the N layers, N can be 3, 4, 5, whatever it is, or can I find an equivalent one? What we do here is very easy to find out. If you can see that the flow is parallel to each other. So can I say that the total flow is equal to Q1 plus Q2 plus Q3 plus Qi and like that Qn. The total flow is sum of the flows. You get the point? Because the flow is taking place through each layer. So can I write it as, and the total flow I say is equal to here K average I into area. Area is the total thickness here into unit distance, because the dam is going to be very, very long. So I take 1 meter perpendicular to the board. So here, what will be the total thickness? I'll say H is equal to H1 plus H2 plus H3 plus Hn, the total. So I would write this as K average into I into H into 1 is the distance perpendicular to the board. It's equal to K1. I is the same because the flow is taking place. The head loss is the same for every layer and the distance is the same. So in this case, I is constant and H1 into 1 plus K2 I H2 into 1, so on. So I can write this as, for flow parallel to stratification, Q total is equal to K average into I into H is equal to, I'll write it in a short form, I going from 1 to N, Ki, gradient is the same, into Hi. It's also implied that the distance perpendicular to the board is 1 meter, so it's understood. If I can cancel I, you can easily derive K average for the horizontal flow along the stratification is equal to sum of Ki into Hi divided by total thickness, which if you want you can write it also as a summation sigma I going from 1 to N Hi. What is the total thickness? H1 plus H2 plus H3 up to Hn. So that's what the denominator is. What is the numerator? You are weighting or adding a product of coefficient of permeability times the thickness. We call this sometimes as weighted average. So for flow along the stratification, you can easily get the equivalent average permeability along the horizontal direction. What happens now if the flow is perpendicular? Now we are saying the flow is perpendicular to the stratification. In this case, if I take a small section, you can see that the Q will be same in all the flow channels or paths. Whatever water is passing through this channel, Q1, Qn, has to be the same here. So I would say Q is equal to Q1, Q2, Qi, Qn. This is called the continuity condition. The flow has to be same. Whatever water goes in at any layer will have to come out from the other side and go on continuously. But what then happens is, suppose the total head loss is H from top to bottom, the loss can be different in each layer depending on the permeability, Hi, H4, H3, H2, H1. The loss in head in each layer is different because the permeability is different. So what we find is this is equal to, if I want to write it, V, cross-section area is the same. So velocity in each layer is Ki, Ki, Ii. Ki is the coefficient of permeability ith layer, and the head loss is Hi divided by the thickness, because what is the distance through which it has to flow? It is Hn, Hi, H4, etc. These are the distances, and this is the head loss. So the gradient could be different in each layer, and what we find here is the velocities are the same because the discharge is the same, but the gradient is different. So can I now calculate Vi is equal to Ki into Hi? So Hi is equal to Vi into Hi by Ki. And what is the total head loss? Total head loss is H is equal to H1 plus H2 plus H3, like that till Hn. And here is what we say, for the whole medium, Q is equal to K average total head loss by H is what we would like to write. This is into, of course, cross-sectional area, or can I write it as K average in the vertical direction for vertical flow and H by H. Let me write it again. For the total stratum, the velocity is given by K average, and please remember the flow is perpendicular, total head loss is H, and the total thickness of the stratum is H, capital H. So can I say head loss is equal to KAV into H is equal to V into H by K average. For each of them, each layer Hi is Vi into thickness divided by, and now if I now substitute here, H is equal to K average is the sum of all the head losses. So Hi, I going from 1 to n, I would like to write it as V Hi by Ki sigma I going from 1 to n. Okay, V is cancelled, velocity is the same. So what you will have is K average is equal to total thickness, which is divided by Ki by Hi, I going from 1 to n. So now you find the equivalent permeability for stratification in the vertical direction. What we found earlier was along the stratification. So now we know how to calculate the two permeabilities, equivalent permeabilities. And please remember, when you calculate K average horizontal, that is along, and K average vertical, that is perpendicular to stratification. These will not be equal. I can say they won't be equal. You will get different values. So this is how we find for stratification. In case you find continuous variation, you should divide this into number of layers and do exactly the same